Okay, so that concludes our discussion about higher order derivatives. But so far we have only looked at what are called initial value problems. So whatever extra conditions were given along with the differential equation, they were always at the starting point. So if you think about it as a graph, this is x of t which we are trying to find out from the differential equation. We knew uh, sorry, t over here, x over here. So at t0 we knew what was x0, and then we knew when you take a small step how much does x change, one more small step how much does x change. That's how we tried and figured out what is x of t. That is basically how we solve the differential equation. Question is, what happens if you're not given the initial value but you're told the final value? Or in term, let's say you're given let's say you're solving a second order differential equation. So d2x by dt square is some f, and now you need two conditions, and instead of being given the x and the dx by dt at the first point, you are given the x over here and you're given the x over here. So you know what is at t equal to 0 x equal to x0, and at t equal to y0, let's call it t0, and when t is tn, then x is xn. So you're given these 2 points, you know this point and you know this point, and now you have to try and solve the differential equation between these 2 points. So how do you do that? So that's what we're going to talk about next. So this is the discussion on boundary value problems. So just as a simple example, let's consider the differential equation d2x by dt square is minus omega square x. You might remember from your 12th standard physics that this is the equation for a harmonic oscillator. So you're thinking of it as, let's say, there is a pendulum. And this pendulum is oscillating. So the deviation from this central point, this is x. And you're asking, as time goes by, how does x keep changing? Omega is the frequency of this oscillation. So this is your simple harmonic oscillator. So you need two conditions because this is a second order differential equation. What kind of conditions can we have? So you can either have initial conditions. So initial conditions would say that, so suppose I'm starting at t equal to 0, I'm starting from this extreme point over here. So let this be x0. So initial condition would say at t equal to 0, x is x0, and the first derivative, so this is just the velocity with which it is moving, and if you remember, at the extreme end of the oscillation cycle the velocity is 0. So if I specify these, that at t equal to 0 x is this and dx by dt is this, then these are initial conditions. But on the other hand, I could also give what are called boundary conditions. So I would say at t equal to 0, x is x0, and now I don't specify the derivative at t equal to 0. Instead I go to some other t. At t equal to t, let's say t is the period of going from one end of the pendulum to the other end, so until it comes here. So over here you will notice x is minus x0 because it has gone to the other side. So at t equal to t, x is minus x0. So these are also two conditions, but they're not position and velocity conditions. They are two position conditions, one in the beginning, one in the end. So this is a boundary condition problem. If I'm given this differential equation along with these two conditions. So this is the problem that I want to solve. How should I do it? All the techniques that we've learned so far, Euler, uh, Runge-Kutta, coupled Euler, coupled Runge-Kutta, these are all applicable only for initial value problems. So what we'll try to do is we'll try to convert a boundary value problem into an initial value problem. And then we can use all our existing methods to solve it. So in order to do that, we will use what is called the shooting method. So I already have my differential equation. And I have my boundary conditions. What I will do is, I will try to guess what should be dx by dt at t equal to 0. So what I will say suppose I have this system of equations. Suppose I have d2x by dt square equals minus omega square x, and the boundary conditions equal to 0, x is x0, and at t equal to 0, dx by dt, let me call it some v0. So v0 is some value that I'm guessing. Okay, I'll take any value that I feel like. Now this system of equations, this is an initial value problem, right? So I can solve this initial value problem in the same way using Euler or Runge-Kutta. And by doing that, I will try to find what is x at t equal to t. If x is exactly the same as minus x0, this is what I want. This is the second condition that needs to be satisfied. So at t equal to t, if I find that x is minus x0, then my work is done. But if x is not equal to minus x0, that means my initial guess of v0 was wrong. So I'll try with a different value of v0. So now try with v1. I'll see whether I'm getting x equal to minus x0. It still doesn't work, then try with t2, with v2, and so on. Now you might think this is kind of stupid, that I'm basically just doing some random guesses with different velocities v1, v2, and seeing which one gives me the correct answer. But you can do it more systematically. What we are basically doing is we are trying to ask the question, for what value of v is dx by dt, no, for what v is x equal to minus x0 at t. And this is exactly a root finding problem. So what I'm saying is, for every v that I choose, I can calculate so such that dx by dt is v. From this, I can use Euler or Runge-Kutta to find x of t, and I have to check that x of t should be equal to minus x0, or x of t plus x0 equal to 0. So I'm finding the root of this equation, and this equation depends on v, because x of t that I have got, it depends on what the value of v is. So this is exactly a problem in root finding. We have learned methods of root finding: bisection method, Newton-Raphson method, secant method, and so on and so forth. So you can use any of them to find the root. You want to find that particular value of v which will satisfy this equation, basically which satisfies this boundary condition. So by doing that, if you find the value of v in that manner, then you will have found out exactly that initial condition, dx by dt equal to v, which will convert this into an initial value problem, and then you can solve that using Euler or Runge-Kutta, and that will give you the solution of x of t. Now, which root finding method would you use to do this? Should you use Euler? Should you use bisection, Newton-Raphson, secant? You will notice that over here you don't know how x of t depends on the velocity. It's not a straightforward way of it's not a straightforward function. So x v of t has some complicated dependence on the velocity. So it's not easy to find the derivative. So it may not be the best idea to use Newton-Raphson, because Newton-Raphson requires you to find the derivative. So for something like this, it may be easier to just use the bisection method. When we did root finding, we saw that bisection method was not the best one for finding roots. Newton-Raphson had much smaller error. But here is one example of a situation where you're actually better off using the bisection method rather than Newton-Raphson, simply because you don't have access to the derivative of the function. You only have the value of the function at various points, at v1, v2, and so on. So you can check whether xvt plus x0, is this positive at some point and negative at some point, then the root has to lie between them. Then you reduce your interval some more and you see whether the root lies between. So that is bisection method. So by using bisection method, you find out at which velocity you are being able to satisfy the second boundary condition that was given to us, and then you have reduced your boundary value problem into an initial value problem. Then it's straightforward to solve this differential equation. So that is the shooting method for you. Okay, the last problem that I want to discuss is the eigenvalue problem. So for this, once again, I'm going to look at an oscillatory example. Let's consider a stationary wave. So stationary wave, if you remember from your 12th standard physics, is a wave that is stuck between, let's say, two rigid walls. So let's call this direction x, this direction y, and the differential equation for this, which is called the wave equation, is given like this: d2y by dx square is minus k square y. And now what can you say about the extra conditions that you need? You know, so let's say this is x equal to 0 and this is x equal to L. Then the conditions are that y, when at x equal to 0, y is 0, because over here there is no oscillation. And similarly at x equal to L also, y is equal to 0. That's at this point. So at the two endpoints, there is no oscillation because it's stuck to a rigid wall. And in between everywhere, you can have some amount of wave motion. Okay, so This is a boundary value problem. And if you want to solve this, you have to convert it into an initial value problem. And to do that, we can use the shooting method. Now, okay, let's go back one step. Why do I call this the eigenvalue problem? In your linear algebra, you have probably seen uh, eigenvalue equations involving matrices, and we also discussed that briefly in the last lecture on matrix methods. So over there you have seen eigenvalue equation which looks like this: some matrix times some vector is proportional to that vector itself. So this is the eigenvalue equation. Why do I call this also the eigenvalue equation? So I can call this operator some d, and suppose I refer to this constant minus k square as lambda. Then this equation becomes d operating on y is equal to lambda y. So this is same as your eigenvalue equation. Only thing is over here, this is not a matrix equation. This operator over here is not a matrix operator, it's a differential operator. But still, all the properties of that you learn in linear algebra, they still hold. So this is your eigenvalue equation. Important thing to note over here is that this is necessarily a linear equation. So this does not depend on some y square or e to the y or sine y or anything. It just linearly depends on y. What that means is that if you take y going to some alpha times y, where alpha is some constant, then this eigenvalue equation still holds, because d2 dx square of alpha y is just alpha times d2y by dx square, and similarly minus k square times alpha y is just alpha times k square of y. So d of alpha y is equal to lambda of alpha y. So if y is an eigenvector of this equation, then alpha y is also an eigenvector of this equation. Or in other words, if y is a solution of this differential equation, then alpha times y is also a solution of this differential equation. Okay. So now let's see what happens if we apply the shooting method to this problem. Now what does the shooting method say? First of all, I don't know. So I'm trying to find this function over here which defines the wave. I don't know it yet. So the only thing I know right now is that at x equal to 0, the wave has to start over here, and at x equal to L, the wave has to end over here. That is all I know. I have no idea what's going to happen in between. That's what I want to find out. So shooting method says that you start with some guess of what is going to happen in the beginning. So you assume some kind of dy by dx, and then you propagate it. You use Euler or Runge-Kutta to see what this gives you. So with x equal to 0, you're saying y equal to 0 and dy by dx is some v0, and we'll see what happens. Suppose as a result I get a wave that comes and ends over here. So this is not going to work because at x equal to L the wave is not 0. So I'll say, okay, fine, why don't I try a different value of v of this velocity. Let's try some value v1. But if I choose v1 is equal to some alpha times v0, that is also not going to work, because as we have seen over here, if y is a solution of this equation, then alpha times y is also a solution of this equation. And here close to the origin you can see that y is basically going to follow what dy by dx does. So if you're increasing y by a certain factor, then dy by dx will also or the other way around. If dy by dx increases by a certain factor, then y also increases by a certain factor. But over here, if you are not hitting 0, you're hitting some finite value, let's call it y prime, then even if you scale up your y, you are not going to hit 0. You're going to hit some alpha times y prime. So if you start with one guess which is going to give you a 0, which is not going to give you a 0, any other guess is also not going to give you a 0. So your shooting method is going to fail. And the reason for that is that this is a linear equation where if y is a solution, then alpha y is also a solution. So what does that mean? Then how do we get a solution? What we are saying is that in this particular case, you cannot convert your boundary value problem into an initial value problem. And the reason for that actually is that this differential equation will not have a solution. That's a profound statement to make. So I've said d2y by dx square is minus k square y with the condition that at x equal to 0 as well as at x equal to L, y has to be equal to 0. This, if it doesn't work for, so given any arbitrary value of k square, if this is not working for some y, it will not work for any y. And the reason for that actually is that this equation does not have a solution for any arbitrary value of k. Or if I put it in a different way, this differential equation, and when I say differential equation, I mean including all of these, including these boundary conditions. This differential equation has solutions only for specific values of k. Physically, what does this mean? Physically, what it means is that only those solutions will work for which you have a node at both ends, and that you have seen already in your 12th standard physics. So this solution works because it has a node at both ends, but this solution would not work because you cannot have this. In other words, you had seen that the total length of this string L had to be an integer multiple of half wavelengths, and that is exactly the condition over here. So this only works for specific values of k such that k equals n pi over L. So if for any arbitrary value of k, you will not be able to do this kind of conversion from boundary to initial. However, if you vary your k and you check whether you are being able to convert your boundary condition into an initial condition, that will in fact tell you what are the allowed values of k. And this is the eigenvalue problem. It basically says that only certain fixed vectors or eigenvectors, which are the solutions over here, are valid. So those are the eigenvectors that you will get. In fact, this reason, the fact that you are only getting only certain discrete values of k are allowed, this is of great importance when we start doing quantum mechanics. So for example, in quantum mechanics, like most bounded systems have quantized energies, or quantized states in which they can exist. So for example, if you just think of the example of the hydrogen atom, and in your 12th standard you have studied the Bohr model of the atom, in which the electrons can only exist in certain energy levels around the nucleus, given by n equal to 1, n equal to 2, n equal to 3, and so on, the orbits. So quantum mechanics explains that exactly in this form, that only certain discrete values of k are allowed, and it has to do with properties of the wave equation when you have fixed endpoints. Okay, so that concludes our discussion on solving ordinary differential equations. Of course, this is not the last word. There are lots of other methods also that one can use. There is one very useful method which has a lot of applications. It's called the Buller-Stower method. You can have, so all the methods that we used, we took from t0 to tn. We divided this into large number of steps, but each of these had a fixed length h. That again need not be the case. In the same way that we discussed in the context of numerical integration, you can have methods which make use of adaptive step size. So you can change the step size depending on uh, what your function looks like. Various other methods. Also, so far we have only talked about ordinary differential equations, but a wide number of possible methods also exist for solving partial differential equations. So it's a huge field, and because how widely applicable differential equations are, you can find lots of different methods which can be used for solving them. But we'll stop here.